A high-producing modern dairy cow is a metabolic anomaly. At the peak of her production cycle, she can yield over 45 kilograms of milk in a single day. Sustaining this immense volume requires a precise, highly coordinated biological transformation known as lactogenesis. Lactogenesis is the strictly defined process by which the mammary alveolar epithelial cells, the specialized secretory tissue inside the udder, acquire the ability to synthesize and secrete milk. Industry shorthand often suggests that a cow begins lactating the exact moment she gives birth. The biology dictates a different timeline. Lactogenesis actually occurs in two distinct physiological stages. Stage 1 consists of partial cellular differentiation and limited fluid secretion that begins well before parturition. Stage 2 is the onset of copious, high-volume milk secretion that occurs right around the time of birth. The biological mechanisms separating these two stages control the cow's massive output and ultimately dictate her survival. During late pregnancy, the mammary gland enters stage 1 lactogenesis. The internal cells undergo partial enzymatic and structural maturation, but output remains tightly restricted. The specific product of this stage is colostrum. It is highly concentrated with proteins and maternal immunoglobulins for the calf, but notably low in lactose. At this point, the physical architecture of the mammary gland is already fully mature. Up to 95% of its lobulo-alveolar growth is complete, leaving a dense network of spherical, milk-secreting alveoli ready for production. The chemical signals required to activate these cells, the lactogenic hormonal complex of prolactin and glucocorticoids, are also actively circulating in the mother's bloodstream. The structural factory is fully built, and the activation hormones are circulating. And yet, the volume of milk production remains at zero. If the gland were to fully activate and synthesize 40 liters of milk per day while the calf was still in utero, the physical pressure and metabolic drain would be fatal to the animal. The cow relies on a specific molecular blockade to actively suppress stage 2 lactogenesis until the exact moment of birth. To see how the gland prepares without flooding, we look inside an undifferentiated mated-wee alveolar epithelial cell. Prolactin and glucocorticoids bind to receptors on the basolateral membrane, triggering a rapid expansion of the rough endoplasmic reticulum. This network pulls amino acids from the blood, synthesizing complex caseins. Simultaneously, the smooth endoplasmic reticulum matures. This organelle utilizes circulating fatty acids and acetate to synthesize triglycerides. These newly synthesized proteins and lipids are packaged and migrate towards the apical membrane for secretion. While this machinery produces the solid components of milk, it does not generate massive fluid volume. The mechanism controlling volume resides within the Golgi apparatus, which synthesizes lactose. Lactose possesses a specific physical property. It acts as a powerful osmotic force. As lactose is synthesized and accumulates inside the Golgi's secretory vesicles, it actively draws water across the membrane into the vesicle from the surrounding cytoplasm. These vesicles reach the apical membrane, fuse via exocytosis, and dump their fluid into the alveolar lumen. Because lactose pulls the water, the rate of lactose synthesis directly dictates the final milk volume. To prevent premature copious secretion, the biology must strictly restrict the synthesis of lactose. Lactose is created by fusing glucose and galactose. The control lies in how they are joined. This reaction requires the enzyme complex lactose synthase. For it to catalyze, two proteins must bind together, galactosyltransferase and alpha-lactalbumin. Prolactin signals the cell to synthesize alpha-lactalbumin, but during late pregnancy, high circulating levels of progesterone actively inhibit prolactin's signal, stopping the synthesis. Without alpha-lactalbumin, the complex cannot assemble, and glucose and galactose are not fused. The lack of lactose eliminates the osmotic draw. Progesterone is a precise molecular safety switch, holding the factory in stage 1 and restricting fluid volume before birth. This biochemical standstill remains intact until the immediate window prior to parturition. The onset of labor triggers luteolysis, the breakdown of the corpus luteum, which causes circulating progesterone levels to drop sharply to near zero. This sudden drop in progesterone entirely removes the intracellular blockade, leaving the lactogenic signals of prolactin unopposed. Prolactin immediately initiates a massive synthesis of alpha-lactalbumin within the epithelial cells. The lactose synthase complex completes its assembly, triggering rapid lactose production and a subsequent flood of osmotic water into the alveoli. This sudden, massive influx of fluid volume marks the official onset of stage 2 lactogenesis and the beginning of copious milk secretion. The sudden activation of this biological factory places the entire animal at the absolute limits of metabolic endurance. The nutrient drain is instantaneous. Lactose production alone abruptly utilizes up to 85% of the cow's total circulating blood glucose. This chart illustrates the energy gap driving negative energy balance. The cow cannot consume enough feed to match her massive energy output, entering a dangerous metabolic deficit. To survive, she undergoes homeoresis, a metabolic shift mobilizing her body fat into non-esterified fatty acids, or nephas. This extensive tissue mobilization allows peripheral tissues to burn alternative fuels, explicitly sparing the limited glucose supply, so the mammary gland can continue synthesizing lactose. The progesterone checkpoint guards lactogenesis so heavily because the biological cost of stage 2 forces the mother to physically milk off her own back to ensure her offspring's survival.